Before going out in the facility, I've prepared some material that will try to explain what we want to see when we look at layup of carbon composites or any kind of composites on structural parts. And structural parts are not necessarily parts which have an aesthetic connotation to them, but more importantly, they have to be structurally more efficient, and therefore the layup of the fibers is crucial. And there have been some questions about the way DD material, which is got shallow angles like plus minus 30 degrees or 050, in which one axis will be one fiber will be laid up at 0 degrees and the other fiber will be laid up at 50 degrees. Those have any issues in pliability, and I'm going to demonstrate to you that is not the case. DD is more pliable than any other material that you have today, and that is for structural components. So let's actually discuss. Suppose this is what basically is pliability. So basically, this outside lines, these represent a surface, and at any point in the surface you have to define a surface, you have a normal, which is this W, and U and V vectors. Normally a NURB surface, which would be any surface that you would use in any structural component, would be represented in NURBs, and a NURB surface is non-rational uniform B-splines. But over here, to simplify, I'm just showing you that it has in plane U and V vectors. These are in plane, so when it comes over here, the angles will change based on the normal and of that point at which you're going to take these normals. Our idea is to make sure that this U or the V follows a certain direction of the vectors, because this any patch in the surface should have the angles in the directions that you have intended them to be, because this each small patch in that patch would be a virtual space in the virtual area on the surface, should have the angles of the plies correctly placed based on the calculations of strength and stiffness that you have envisaged for this piece of structure. So that is the reason why U and V are very important. Now, normally you would place a tape on this, and I'm assuming that tape could be even a very wide section of cloth, could be 1 meter long, or it could be width of about 10 millimeters. That doesn't matter. Basically, we are trying to place this tape, whichever width it is, on a complicated on a contoured surface, as you can see over here. Now what happens is that, suppose you place this tape on the surface, okay, the center line of that tape would be at this U and V angles, at this U and V vectors. Along the U vector, for instance, you consider the U vector to be the 0 degree angled vector, and you place this entire tape along that vector. What will happen is that any distance from that vector, the tape width will be exactly the tape length will be exactly the same as the as the integrated length of this curvature over here. However, if the surface is doubly contoured, so that means that it has a curve here as well as a curve here, what will happen is that this length, the edges, the extremities, these L1 and L2, will be different than the one in the center. And to demonstrate this, I'll show you what I mean. You look at this. So assume that this is the surface on which you're placing it, okay? And if you're placing it on this surface, at the center line, you have this U, which is in the direction of 0 of this tape. But here it is lifted up a little bit, and here it is lifted up a little bit. The reason why it is lifted up is because this length is a little longer than the length that is required for it to drape over this surface. And because of the fact that these fibers are put together, are held together with some sort of a hot melt adhesive that doesn't give it the possibility to lay flat, this will stand up. And now suppose you apply vacuum over it and close it. What will happen is that this length is longer than the length of the U's along this surface's integrated curvature. So what will happen is that there will be kinks, because if you have a surface, if you have any surface, and you try to put it if you have any tape and you try to put it on a curvature which is in which this length has to reduce, okay, and this length is longer, and you force it, what will happen is this excess material, which is because of the longer length, will eventually crimp, and it would crimp down on this surface in a very random manner, and there's no control over this. So if there is no control over this, what happens? You get a terrible edge on each tape. Now suppose you use a very fancy automated tape layup machine or fiber placement machine. Fiber placement is different, but let's say automated tape layup machine. What will happen with the automated tape layup machine is that these edges will always have a spring back and will be away from the surface if it is a convex surface, and if there is a concave surface, they'll be bunching together. You cannot avoid that. You cannot avoid that. So what people say that you can heat the tape at that point in time and press it against this. That would work to a certain extent if there was convex and concave contour of approximately the same length, because what will happen if you try to heat this hot melt, there will be excess material that would form on the side of the rollers, and that excess material will not stick along this properly, because when you stretch it over a surface, the stretch should be something like this. So this should be the amount of stretch. That means that this curve is following the ATL machine is following this curve on the mold, and if it is curved convex, then this side you will have to, and you started off like this with a rectangular end over here. At this end you will have to stretch this fiber more, because the length at the bottom is smaller. If the length that this has to be placed onto is smaller, the excess material has to be pulled out, and that is what it will be. That is how it would happen. Now you cannot control this curve. You cannot control this curve on complicated surfaces very accurately if you have a fixed width of the tape, unless and until the concaves and the convexes balance each other. So you have the same amount of concaves and same amount of convexes on each layup, and that would mean that you're actually laying up on a sphere or a bowl which are put together. But that's not what people do. People are laying it up on wings and fuselages which have surfaces which come together. So this is about tape, and we have something that we are going to show you just shortly. Now, as far as cloth is concerned, cloth will lay up very beautifully on this without any problems. But the cloth has a big problem, and the problem is that its compressive strength and compressive stiffness is abysmal compared to structural components made from NCF, which is non-crimp fabric. And when we talk about DD, we are talking about non-crimp fabric. And that abysmal strength actually comes from the fact that cloth is woven like this. And when it is woven like this with one weft or a warp of the cloth coming with a wavelength of about 1 to 2 millimeters, because there's a piece of strand of fiber over here, there's a fiber strand here, then there's this fiber strand going up and down across those strands, and there's also a strand here. So this thing, if it is put into any kind of compressive load, it's already buckled, it's already bent. So when you apply compressive load to it, it just goes, it doesn't have any compressive strength. Now, most of the composite structures are loaded in, their failure criteria is in compression, because in compression, compression is the, they have a lower strength in compression, most composite materials. So if they have a lower strength in compression, this is a type of material you can only use for aesthetic appearance. You cannot use it as a structural material. Now here we are only talking about structural materials, although aesthetics is important, and I can show you how beautifully you can use some other type of material in order to get a pleasing aesthetic surface for curves which are not for surfaces which are not very highly contoured. You can get very pleasing surfaces from tapes. But the best aesthetic appearance you would get is from twill, which is this kind of material, which is cloth, woven cloth, but it has 0 to nil compressive strength. And if you use something like this, you are adding excess weight to your structure. The other thing I'd like to talk about in a few minutes when we go outside in the facility is that we're going to talk about spread to material with a plus minus 30 degree DD, and we're going to show you the glass twill. These are the three things we will show you on a ball, and we will show you how this thing works, and that you get crimping at the ends of these tape edges if you are on a convex or a concave structure. If you're on a concave structure, you would have crimping in the middle, and the outsides would be flat. And if you are on a convex surface, then you would have crimping on the edges, and the center would be flat. Whereas in a spread to material, which is DD, you have absolutely no issues, because there are single strands, like this, okay, which are along the U, and there are strands at an angle. So if you have the fiber angle like this, and you call this phi, and you have another fiber angle like this, and you call that psi, that's what a DD is. So a DD has one angle in one direction from this U, and one angle in another direction with respect to U. So now we're showing it over here like this. So this could be 0 degrees, and this could be 30 degrees. So this 0-30 degrees will lay up really flat on any kind of material. The reason is that it is not prevented by sliding. It's not preventing any kind of sliding between these different layers, between these different fibers, because they are stitched together. So if you lay them, they will lay flat, and they will stretch in the areas where you need it to be stretched, and they will they will, you have to lay them from the shortest direction, not the direction of U, but basically if it is a concave surface, you'll make sure that the edges are first laid down, and then the center. If it is a convex surface, then you have to make sure that the center is first laid down, and then the edges. And once you do that, this will lay flat, because it would stretch in the process of laying up. And that is the cool thing about DD. The cool thing about DD is that once it is laid up and it is laid flat, and then you pick it up, it will stay stretched like that, because the fiber is actually sheared between the stitches. It has actually shifted and slightly, and it is held in that place because of the stitching over there. And the stitching, I will show you how it works, and it's very, very easy to lay up. So what does the stitching do? It is a 2 gram per square meter or something like that stitching. It is through the thickness stitching. It gives you extremely high toughness of this material. It gives you easy layup and very, very easy pliability of material. This kind of layup and pliability is not there in any other kind of material that we have seen. Of course, the satin weave and the double twill weave of regular cloth will give you very high pliability, but they are not structural. And that is where DD or any other NCF, that is non-crimp fabric, will give you very easy pliability. It's not just DD. Any non-crimp fabric will give you very easy pliability, and it'll give you a very strong surface which has extremely high compressive strength. So now we'll go outside and I'll show you what I mean. Okay, so welcome to NASHERO, and that is my company which makes small airplanes, and we're trying to show you how tape laying would work, and this is based on the explanation that I gave you in the notebook a few minutes back. And we are going to use in this experiment, we're going to use a bowl which is a semi-sphere, both from the inside as well as from the outside. And this is how we'd like to show you how the pliability between regular material, that is twill, spread toe material which is made from tapes, and the DD. So let's get on to it as quickly as possible. Let me describe the material to you first. So this is twill, and this is a woven cloth in which the fibers are in this direction and in this direction. So this would be the zero, and this is the warp, and this is the weft of the material. And you see, this is the knitting of this material is very close to each other. However, this is a 2x2 twill, in which that means that it leaves two strands before it goes on the other side. So before it goes up, there are two strands across which the material goes like this, and the same thing is on the other side. Now this 2x2 twill is got a lot of give, and a lot of give would mean that this material, if you hold it like this and you stretch it, you see that it shears. You see that it shears. So it stretches, and it's not the material that is stretching. Glass and carbon both are extremely rigid fibers. They don't stretch. The stretching is between the placement of the fiber with respect to each other. So these axis fibers and these axis fibers, they slide among themselves, and that is what I mean by stretching, and that is what I mean by shear in the cloth. This is not the shear of the fibers. This is the shear of the placed fibers between themselves. Okay, so the material is not shearing in the sense of an isotropic material shearing like this between it. It is this in-plane knitted material that shifts in between the placement of themselves, and that is what I mean by shearing, and that is very high in this. You look at this material here, okay, and this is spread toe material. In this, what is done is that a very thick fiber bundle is spread using air, and then on the other side, on one side it is nascent, on the other side it has a very thin spray of hot melt glue. It's very small amount of material, like about 0.5 grams per square meter, and that holds this thing together, but it just holds it very lightly. The problem with this is that it doesn't have any shear between the bundles. The bundles will break apart, although the fibers will not break, but the bundles themselves do not allow any shearing in the layers over here. The shearing can only happen between one fiber tape and the other fiber tape. So if you try to shift it, you see that it doesn't shift at all. Now here we have taped one end so that it doesn't come open, and this side is stitched as it was stitched when we received this material. And I'm going to show you how big of a menace it is to put it on a dome shape like we have over here. Now here we have plus minus 30 degrees of DD. As you can see that if you consider these lines that you see over here, these lines going in this axis, in this direction, these are lines of stitching, and these are made from polystyrene, or I think some sort of a polyester material, and and they are stitched through the thickness. This material is stitched through the thickness, and on the other side you would see the same stitches coming across. Okay, this is stitched, and the fibers in this, you see them at this angle. If you look carefully, I hope it focuses, you can see the fibers are in this angle. You can stop this video and try to look at this. The fibers are in this angle, and at the bottom the fibers are in this angle, but when I turn it around you will see that they will be in this angle again. Okay, because one is in this angle and the other is in this angle, but when you turn it around, because of them being symmetric, you will see that that they turn around. So this is basically what non-crimp fabric is. In the non-crimp fabric, all the fibers are in one axis, and they are stitched together in one layer. They are in one axis, and they are stitched together through the thickness stitching, as you can see over here. This stitching has two very useful roles. One is to hold the fiber together, and it increases the toughness of this material if it is made and then laid up in composite material, and then you drop a ball on it to see the toughness of this material. This prevents the premature splitting of the fibers because of through the thickness stitching that you see over here. And this will have a stronger, will be tougher than material which is just plain laid up one axis in this direction without any stitching, another axis in this direction without any stitching. So basically, if it is plus minus 30 degrees and it is made from uniaxial tapes, like some of the bicycles are made, they will have less toughness compared to this. But there, basically, toughness is not important. It is the strength that is important. In strength, they will be exactly the same. But in airplanes, toughness is very important, and that's why this is a better material for our application. So let me just quickly show you what I mean by pliability. And I will show you the most pliable material that is there. And I told you that the most pliable material is twill, and we have a twill of glass. Now you see that I'm trying to lay it up across the center, and you see that this edge is up in the air. And if you recollect, the reason why this is up in the air is because the place that it will be laid up on this surface has a smaller length. If you make a section over here and measure the length of this surface, it is smaller than the length over here. And that is why, because right now the material has not been pressed on it, and we haven't coaxed it in any of the corners. So the material is held in a manner in which because of its inherent strength or inherent resistance to shearing, that is shearing between the various fibers that you have in the cloth, it is held constant. Now I coax it slightly, and you will see that it is already laid up along that curve. So if I coax it slightly, so I'm coaxing it slightly, and you can see that it is getting laid up without any problems, right? Now if I lift it up from here, you would see that it is perfectly fine. You see that? It has taken the shape of this thing. And if I take it out, you would see that it has already taken the shape of that. Of course, this is a slightly thicker material, and the reason it does that is because there is a certain ability of these fibers to slide among themselves, because there is no epoxy or any matrix in the middle that is preventing it from sliding and from transferring the loads from one fiber to the other. There is nothing there. So that is the reason why it is free to slide, and it does so and takes the space of everything. So now I will show you the layup of this material, and this is very stiff material, because it is connected together by the hot melt glue that I talked about earlier. And you can see when we lay it upon this, when we lay it upon our dome, it actually doesn't want to lay down. It doesn't want to lay down. Whether you lay it down in plus minus 45 degrees or you lay it down in 90 degrees, it does not want to lay down on this thing. Now suppose we press it here, nothing happens. If we press it down here, you know that as I explained to you, this length of the material is longer than the length which would be projected onto the surface by this edge. And the only place where it is going to lay down flat is the center. But however, let me also show you that, so this is impossible to lay up. And believe me, we have had a lot of issues with this material laying up. Now suppose we have this material, let's try to lay it up like this. And let me do a zoom, let me zoom it so that you can see the, let me zoom it first so that you can see what I'm talking about. Okay, so here we are. Now this material, I'm trying to put it flat on this curve. This curve is very gradual for such a narrow piece of material. But here also you will see that I press it here, it is lifting up from the edges, and the same thing is here. Now actually, because I'm holding it at this end, so this end is flat, but this end is lifting up because it cannot follow the curvature. Suppose you press it down on the center, and you leave it on this mold for vacuum bagging. Eventually you will have micro imperfections due to compression failure, due to compression over here, due to crimping of this fiber at this end. And I think that it has gone out of focus. It has gone out of focus. Yeah, here you are. So basically what I was showing you is this. Now here, if I press it, you see that it is lifting up. It's not sitting flat on this material, right? It's not sitting flat on this curvature. And suppose you lay it up and vacuum bag it, you would see that this edge would crimp and this edge would be flat, and that is not what you want. You want the entire surface to be flat. So that is why that kind of material is a menace to put on, and we avoid that. Now let us look at the pliability of DD. So here's DD, and let us zoom out a little bit to show you what we mean. So this is DD, and here you see that we haven't taped it anywhere. Okay, there is no taping on the edges to prevent fraying. We needed to tape the edges of this one to prevent fraying. Okay, and we would also need to tape the edges of this to prevent fraying. As you can see, it is fraying all over there and here also. So you'd have to tape it. Once you tape it, it'll not move from there. So you have to tape it in a manner in which it allows it to lay up. Now here you can see the classic example of what I was trying to demonstrate to you. This is the same width as the others, and now it is sitting as if it's not going to move anywhere, right? So it is actually like a flat sheet which has been bent. Now it is not a flat sheet, because the moment you try to coax it, these fibers will slide along the stitches. So they will become, they will expand or they will contract, and they have a little space in between them. As you can see, the stitching is pretty close, but it allows it to have a certain amount of give, and that give is what will allow it to take the contour as I coax it into the edges. And you can see that it actually forms the edges without any problems. Very, very small amount of coaxing will make it move and will allow it to take any kind of space that one may want, any kind of shape that one may want to give it. And you can see I haven't done anything much. I've just placed it on this and given a very smooth touch. And you can see how well this is better than the twill material that I just showed you. So here, if I take it out of this, it will retain the shape much better than the twill material. You see that? So this is how pliable this material is. Now, as you can see, and you'll realize that if we have larger angles over here, those larger angles will sit on a curvature even better, because they have less angle to bend, to conform to the contour. On the other hand, if you have a plus minus 45 degree over here, it would behave almost exactly the same as this. And if it is non-crimp fabric, which is this kind of material, it will lay down without any problems. This cannot be said of other materials. The biggest advantage with DD is that when you lay up DD, you lay up with exactly the same repetitions of the angles. So you could take a bunch of this material, cut on your automated cutting table. You can place it and you can spread it out, coax it by one simple move, and they will all sit properly. If you have, on the other hand, a legacy quad which is 0, 90 and plus minus 45, and these layers are thin, so maybe you have to put first a 0, 90 and then a plus minus 45, then a 0, 90, then plus minus 45. Because plus minus 45, you'll have to turn the direction of the layup by a certain angle. You will have to coax it in a different manner. You cannot use an automated process of coaxing it into the mold. And this is one big advantage with respect to multiple layers of legacy quad put on a mold with respect of non-crimp fabric. I'm talking only about non-crimp fabric now, of non-crimp fabric. So this is the big advantage of DD non-crimp fabric with respect to the other. And I think I have given you pretty exhaustive understanding of how this can lay up in a curve like this, and this is not a typical curve that we would work with. Our curves will be far more complicated than this curve. But you can see the DD, no, our curves will be far more gentle compared to this one. And if DD can lay flat on a complicated, extremely high curvature curve like this one, for a wing or a fuselage, it has absolutely no issues. So I hope you enjoyed this and you learned something out of it. And if you have any questions, and you would like to us to explain you something further, please let us know. And if you want any components to be made from DD non-crimp fabric or anything composite using our special zero void technology, we have an infusion process which is capable of giving you zero void content, and that increases the material's fatigue life almost infinitely, makes the fatigue of that material almost impossible, because there are no discontinuities or stress concentrations inside the matrix, because the matrix doesn't have any voids. So if you want any components to be made with that technology, please contact us for structural parts or even with very high aesthetic appeal, and we'll be very happy to make those for you. And we also do 5-axis machining of titanium inserts and titanium components and aluminum and steel components of very large sizes, and we can incorporate them inside the composite material as embedded parts. So if you wish, you can contact us at the address you see on top.